Hi everyone, welcome to the Climate Confident Podcast. My name is Tom Raftery, and with me on the show today, I have my special guest, Matt. Matt, welcome to the podcast. Would you like to introduce yourself?
Absolutely. Thanks, Tom. I'm Matt Harper, Chief Commercial Officer and one of the co-founders at Invinity Energy Systems. Invinity make vanadium flow batteries for long duration storage, and we're looking forward to telling you all about what that means.
Fantastic. So let's start off with a quick battery 101, Matt, because most people here would be familiar with lithium-ion batteries. They're in our phones. For some of us, they're in our cars, but vanadium flow batteries, not so common, I gotta think. So what is a vanadium flow battery and how does it differ from a lithium-ion battery?
So, great question. So, fundamentally, what a vanadium flow battery does, or what there are a number of different classes of flow batteries, but what a vanadium flow battery does is it takes the portion of a battery that generates power and the portion of a battery that stores energy and separates it from one another. So, those two things are conjoined inside a lithium ion cell. We construct them separately from one another. So the power generation in one of our batteries is in a device called a cell stack, which is a series of electrochemical cells that allow the battery to charge and discharge, whereas the energy inside the battery is stored in a liquid electrolyte. That liquid it's fundamentally it's battery acid with dissolved vanadium in it, hence the vanadium part of the name. And in order to help that charge and discharge reaction happen, the liquid electrolyte it flows through that cell stack, hence the flow battery portion, as a way of fueling, in effect, that charge and discharge reaction. What that separation of those two things allows us to do is it allows us to architect from the ground up a battery that has some really unique and interesting characteristics. The most important one being that we can go to very long durations of storage at comparatively low incremental cost. If we want to go from a 2-hour to a 4-hour battery, for example, really we're just increasing the volume of liquid that is inside one of those batteries. That means that as the grid needs longer and longer duration storage, we can provide that comparatively inexpensively. The other benefit is that in one of our batteries, the charge and discharge reaction happens exclusively in that vanadium liquid. And what that means is that if you look at the charge and discharge mode inside a lithium-ion battery, and you look at how those batteries degrade over time, fundamentally in a lithium battery, what you're doing is you're plating material onto an electrode and then tearing it off again every time you charge and discharge. With one of our batteries, because that charge and discharge happens totally in a liquid, we don't get that very small degradation over time. Over a cycle or two, you would never notice those changes, but over 1,000 cycles or over 10,000 cycles, it means that while other battery technologies are going to degrade, we don't see that sort of degradation mechanism inside one of our batteries. So, for example, installing our batteries alongside, for example, a solar plant, where, if you're going to absorb solar energy and deploy it onto the grid when it's most valuable, you're going to do that over the 25 to 30-year asset life of a solar plant. You're going to be doing that 365 days a year. You're probably going to be doing some ancillary services on top of that. It allows us to do 10, 15, 20,000 charge and discharge cycles without fundamental degradation in the battery's performance. So very much an asset that is developed from the ground up to be fit for purpose for standing alongside renewable power generation.
Yeah, that was going to be my next question, actually. I assume them being, you having liquid as part of the flow battery, not that suitable for cars.
No, and that is one of the downsides of the technology. It is comparatively heavy, so not something you're likely to see in a car anytime soon, not likely something you're going to see in a mobile device anytime soon. With that said, if you look at the number of charge and discharge cycles that a typical vehicle will go through over its life, you don't necessarily need the ultra high throughput, ultra high charge and discharge cycle count that we're able to achieve. And so when we look at the future of mobility and the role that we can play, it's very much more on the infrastructure side. How can we put a battery alongside an EV charging station that in the morning and evening rush hour is going to be able to supply power to vehicles that are in transit, rather than actually providing power to the vehicles themselves.
Interesting. Yeah, that's a nice use case because a lot of people mightn't realize that in these charging stations where you can have multiple chargers together and multiple cars plugged in, you can either have a big fat cable going into the back of the charging station to make sure that all chargers can discharge fully at the same time, or you can have a smaller cable and a big battery there to supply the power as well. So I can see how the vanadium flow battery would suit that installation beautifully.
Look, it's absolutely true, and the reality is that those big cables into fueling stations today simply don't exist. And if you look at what's happening in the renewable space in general, I think we see all around the world that the biggest hurdle to delivering more renewable power onto the grid in many jurisdictions is the time it takes to make an interconnection into the electric grid. Trying to build those same sort of interconnections on the load side, i.e., into new and expanded electric fueling stations, is something that is going to be a massive drain on the electric grid, and I don't think something that we're going to see anytime soon unless we have batteries on site supporting that fueling infrastructure.
Yeah, because you can trickle fill those batteries in times when there isn't a lot of demand, and then just discharge them as there is the demand. No, it's a beautiful use case. I've heard of a use case for rail as well for similar kind of things, but that's a whole other thing, and we don't want to go down that railway track.
Yeah, lest we get off the rails.
Nice. One of the other limitations of lithium-ion batteries is there's a fear of fire with those. I've read, so you correct me if I'm wrong, but I've read that isn't as big an issue with vanadium flow batteries.
I would say it's a near zero issue with the batteries themselves. I mean, look, any electrical infrastructure has some fire risk associated with it just because of the nature of passing a lot of energy through wires and such. But when you look at the battery itself, our batteries are fundamentally non-flammable. There's a regulatory test in the US called UL 9540A, where you basically need to try and prove that the batteries are not going to, at the very least, start, if not propagate, a fire. And we submitted our batteries to that test, and they essentially they didn't even need to run the test because they weren't able to ignite the electrolyte inside the battery in any way, shape, or form. So, we got a pretty easy pass there. But look, it's absolutely true. And it really depends on the application. I mean, look, nothing in the world is without risk. And I have seen a lot of people talk about how, there's a lot of risk with electric vehicle batteries. I mean, it's true, but there's also a lot of risk with
a tank full of
diesel
petrol
and petrol power. Yeah, exactly. Now, where I think that there is, from our perspective, we see a lot of pushback for battery installations in urban and industrial areas because of the fire risk. If you're building a solar farm out in the middle of nowhere, does it matter if your battery has some risk associated with it? Probably not. But if you are in an urban area, you've got batteries at a substation looking to regulate load into a residential neighborhood, you need to be absolutely certain that there's no risk of fire, there's no risk of toxic fumes being clouding the neighborhood. And so for applications like that, we are increasingly seeing that we've got a tremendous leg up on the lithium-ion incumbents.
What about size? I can imagine there's a weight differential in favor of lithium-ion, but in terms of size, and if I'm thinking about a use case here, it's for home energy storage. So the likes of the Tesla Powerwall, 14.3, I think it is, kilowatt hours, sticks on the side of the wall of the house. But to your point, It's a lithium-ion battery. There's a negligible, but there is a risk of fire there, and there's a lesser risk of a fire with a vanadium battery. So in terms of size, would it be significantly larger for the same kind of storage capacity? And also, would there be a significant price differential between the two? And in which direction would that go?
Yep. Great question. So in terms of the size, and we don't do work today in residential, so I don't have a comparison directly at hand. But if you look at industrial energy storage, for example, the amount of energy source that we put into a 20-foot shipping container as a form factor, for example, yeah, is significant, is less than you would see with a comparable lithium array. Now, the benefit though is because of that lack of fire risk, there's no need for spacing those containers out vis-a-vis one another. So we can take these battery containers and stack them up so that they look a lot like a shipping port,
Right.
directly on top of one another, directly alongside one another. And therefore, the absolute size of one of these installations, depending on how you want to measure that, we benchmark at meters squared per megawatt hour of installed capacity. We are at least as dense, if not denser, than the leading lithium-ion solutions out there today.
Okay, and in terms of cost?
As it stands today, we're probably there's a big range of lithium costs out there. For the projects that we're currently serving, which are sort of the large commercial and industrial and small distributed scale, we're roughly on par. When you get into the lithium-ion mega projects that are being built out, the hundreds of megawatt hours north of that, we are more expensive. We do see that changing over the next couple of years. We are engaged in a joint development agreement with the folks over at Siemens Gamesa to build our next generation product. That is going to put us directly competitive with lithium-ion batteries in the majority of applications. Now, with all of that said, the one thing that I would add to that question is that if you're looking at the initial capital cost of those batteries, what I just said is accurate. But if you want to look at the total cost of ownership of those batteries over their life cycle, and especially talk about levelized cost of storage, which is essentially how much useful work are you getting out of the batteries over their life, we already are significantly better than lithium-ion batteries in the kind of applications we target. And we have a path significantly downwards toward some very, very compelling cost numbers in the long term.
Okay. And is that, I presume that's because the longer life and the greater cycles, the greater number of cycles per battery? Because I assume if you are on a grid, for example, backing up either wind or solar, you're probably doing frequency regulation, which is kind of multiple times per hour or per minute, even at times,
Yep.
depending on when you're called on to step in. And that could mean tens or hundreds of cycles per day at different times.
Yep, that's exactly it. I mean, and we focus on what we think of as high throughput applications. So whether that's, we've got an installation up in the north of Scotland, which is regulating power output from a tidal turbine. So it's doing 4 deep discharge cycles per day, constantly cycling. A very, very difficult duty cycle for lithium-ion batteries to survive. Conversely, a little bit further south in the UK, we've got our installation at the Energy Super Hub Oxford, which is doing a combination of merchant trading on the electricity markets and some of those ancillary services in the broader electricity market there. So each one of those means that in both applications, we are cycling the batteries almost continuously, making sure that we are getting value for our customers out of those devices as many hours of the day as possible.
Fascinating. Tell me a little bit about, just veering left for a second, tell me a little bit about the genesis story of Invinity. What made, you're one of the founders, so what made you kind of wake up one morning and go, I know what I should do. I should start a vanadium flow battery company.
Well, I'll tell you, the real story is that I woke up one morning and realized what I shouldn't do. But we'll leave that one to the side for now. Look, I've been working in renewables since the mid-90s. I spent the first 10 years of my career in hydrogen and fuel cells. And then in 2005, I had the opportunity to go join a company called VRB Power Systems, which was the original licensee of the vanadium flow technology into North America. We sort of went through a couple of corporate changes, a transaction that saw us acquired by a company over in Asia. And in 2013, we were continuing to advance the commercialization and deployment of the technology, but we were really focused on these sort of very, very large scale utility projects, in the sort of tens to hundreds of megawatt hours that were being constructed on site as kind of, bespoke engineering projects, say, kind of built like a small chemical plant. And what we saw was 2 things. First of all, we saw that mode of construction wasn't going to evolve the technology in the way that we wanted, simply because when you build something on site, you never get the degree of standardization and consistency that we thought would be needed to really understand how these batteries operate and how we could optimize them over time. And second of all, we didn't think that that method of constructing batteries was ever going to be fit for purpose for deployment in North America, because at that time the most exciting story in renewables was the massive uptick in solar deployment, and solar plants are being rolled out on the order of megawatts per week. To turn around and say, yeah, we can deliver a flow battery to support your solar plant, but it's going to take 2.5 years worth of site engineering, permitting, and construction, simply was never going to work. So the concept that evolved out of kind of the Venn diagram between those two forces was for us to say, look, could we take this technology that we know really well, a technology that we know will be very much fit for purpose for serving renewable power projects, and turn that into something that's totally turnkey, that we could deliver out of a factory with great quality control at lowest possible total cost, and deliver it to our customers in a way where they could hook it up and have it up and running within hours to days. And that was really the sort of the nut of the idea that ultimately became Avalon Battery, which was the company we founded back in 2013, and that we brought into Invinity when we merged with one of our competitors over in the UK back in 2020. That concept, I think, has been fairly well proven now. We've now shipped, I think the number is something like 1,400 of those individual battery modules into the field. That's more flow batteries than have been built by the entire group of flow battery companies in the rest of the world.
Wow.
It's a huge fleet. And as we expected, what that fleet size has given us is an unbelievably powerful data set that we can go to, and we've got real-time telemetry into most, if not all, of those systems. We get the data back in terms of how they're actually operating, how they're actually performing, critical metrics like uptime, like efficiency, like any sort of degradation over time, round trip efficiency. All those things come back into our data platform, and we're able to use that fleet to fully optimize the current operation and also our future product development. So I think that strategy of sort of modularization and using that modularization to drive standardization, using that standardization to drive ultra high quality and lowest possible cost has been one that's played out very well for us.
Nice. And so if you are getting the data back from the batteries, does that mean that you are also maintaining and managing the batteries for your customers, or is that something that you hand off to them, or is it a mix?
It really depends. I would say in some instances, we directly support batteries in the field. Increasingly, what we are trying to do, especially as we go to much larger projects, we're not the ones who are typically pouring the concrete and running wires and doing all the good install stuff on a particular site. So what we've been moving towards is a mode where we provide sort of the expertise and know-how, and then we use local teams to go and from third-party contractors to go and not only build the facilities in the first place, not only install the batteries themselves when they land on site, but also provide any of the support that might be needed over time. One of the things that our customers and their suppliers, or the people who are providing those maintenance services like about our batteries, is that there's nothing in a vanadium flow battery that will trigger maintenance fairly quickly, right? Because we've got a fairly modular nature. If we see the performance of an array of say 300 of our batteries starting to change in a way that might indicate that some maintenance might be required, that's an activity we can plan for 3 to 6 months out, not where we have to roll a truck to site right away, which can become very, very expensive, as you can imagine. So the nature of the technology is such that we can plan those maintenance activities fairly proactively, and therefore keep that, as I mentioned, that levelized cost of storage as low as possible over the life of the solution.
Okay, nice. Talk to me a bit as well about the market for energy storage, because with the deployment of renewables, it's obviously growing. Also, with the deployment, the increasing deployment of an increasing electrification of transportation, for example, the competition for batteries has got to be growing. I know we're bringing more battery plants online, but for example, for grid energy storage, the utility companies or the people who are building the wind farms and solar parks and tidal and et cetera, they're looking for batteries. They don't care whether they're lithium or vanadium or whatever. What they want is storage, whereas the car manufacturers are not looking for vanadium. So obviously there is less competition for what you guys are producing. That's got to be working in your favor, right?
Yeah, absolutely. I mean, lithium-ion batteries have done a phenomenal job of proving that storage can be a very helpful and, for developers, a very profitable part of the electric grid. But where they've proven that capability, it's at sort of the the pointy front end of electricity markets, where, for example, the kind of prices that we saw in the UK last winter, where people were paying $2,000 or £2,000 a megawatt hour for energy, for example. I mean, batteries can be very, very profitable in those kinds of areas, but it's a limited number of cycles per year, and limited number of hours per day where those numbers tend to make sense. What we are seeing around the world is a progressive shift to longer duration batteries, to higher throughput batteries, and that's driven. It depends on the jurisdiction how that push is happening. For example, in Australia, where we're just building one of our largest projects right now, they have essentially, the grid operator has essentially said, look, we're not going to let you put any more solar generation onto the grid unless you have a way of capturing that solar generation and delivering it back onto the grid when it's more valuable, because they already have negative pricing for electricity many, many hours of the year. Incremental solar is not hugely valuable without having storage available, and indeed is starting to look more and more like a burden to those grid operators. Conversely, we see in other jurisdictions where so that's sort of the operator push. We're also seeing other jurisdictions that are starting to look at different types of direct markets for the battery. So rather than saying, look, you can't install more renewables without a battery, other markets are saying, look, we're going to create market structures explicitly for long duration capacity or zero carbon capacity or things like that, that would directly incentivize the construction of batteries by themselves. Both can work, and we're sort of happy to adjust to what are the stipulations in particular markets are to make those kinds of projects happen. But look, to your fundamental point, competition with mobility, it's absolutely true. I mean, one of the things that we've often thought about is, if you're a lithium-ion battery manufacturer and you could wrap a metal box around your battery and put it in a field, or you could wrap some very sexy, very fast, high-tech piece of automotive machinery around your battery and put it out on the road, which one would you rather do? I mean, the cars are going to win every time, whether it's just from a market's perspective or whether it's from a value add perspective. We think that lithium is going to continue to dominate that automotive space, opening a window for stationary storage, especially as we look towards those much longer duration applications and trying to achieve what is ultimately, we hope, net zero baseload around the world.
Yeah. And talk to me a little bit about that as well, because the idea that the old trope that we always hear, that the sun isn't always shining and the wind isn't always blowing, there are, though, times when there isn't sun, or obviously every night, for example, but cloud cover, intermittent cloud cover, or the variability of wind, and batteries can step in there really nicely. But also, increasingly, we're starting to see, or are we, correct me if I'm wrong, we're starting to see more and more grids looking for, to your point, longer duration energy storage. So is the sweet spot of that shifting in terms of economics? Because batteries are becoming cheaper, solar is becoming cheaper. And so maybe the sweet spot for that was an hour of storage for a renewable generation facility. Now it's 2 hours, now it's 4 hours, now it's 8 hours. I'm not sure where it falls. It probably depends on region as well and the technologies. But is that shifting from shorter durations to longer durations now? And are we seeing more be deployed for that reason?
Yeah, absolutely. And I would, probably the most comprehensive and interesting piece of work that we've seen in this area is the US Department of Energy published a report earlier this year called Pathways to Commercial Liftoff for Long Duration Storage. And what that report looked at, I think, in one of the most comprehensive ways I've seen, is if we look at what the grid is going to be in 2030, 2040, 2050, what percentage of the energy storage on the grid to achieve that sort of ultimate level of anticipated or desired decarbonization will be served by what they call short duration, long duration, and seasonal storage. And if you look at what they are presenting, and I think it's I mean, no models are right, all models are useful, isn't that the old expression? It's certainly they present it in I think a very logical way. um, Shorter duration storage is still going to have a massive part to play. There will always be intermittency. There will always be, connection constraints. There are things that need to be worked around. That middle ground of, where we're focused, essentially, how do you take electricity from the daytime when the sun's shining and push it into the nighttime when the sun isn't, is potentially a pretty big part of it because it's so regular, right? We know that the sun, we get good solar generation in a lot of regions in the middle of the day. We know that we get good wind generation in coastal areas, in the morning and evening. So those are sort of very regular things that we can plan infrastructure around, and we can use to deliver a large part of that sort of total amount of energy needed. But then there's that seasonal portion. How do we make sure that the doldrums of February can be served by the wind power that was generated in the blustery days of November? I mean, those are that is an equally critical capability. What we find interesting is that if you look at the absolute magnitude of energy that is delivered onto the grid, and I would use absolute magnitude as a measure of relative value of energy deployed onto the grid in that future scenario, the vast majority of it is coming from that middle segment, right? The number of terawatt hours that will be delivered onto the grid in a net zero future disproportionately come from that middle ground. More than 10 hours of duration to less than, say, 36 hours of duration. That is the sweet spot for where the majority of that energy is going to come from, and that's where we're really focusing our business.
And is that for reasons of economics or for reasons of there's going to be just more demand for that middle ground than either end?
It's a combination of both. If we look at the economics of our product, the vanadium that goes into our battery is a comparatively large portion of our total product cost. What that means is that we want to be making use of every one of those vanadium ions as much as humanly possible.
Sure.
That means, regularly charging and discharging those devices, making sure that that ultra high throughput is something that means we get very high utilization out of that little asset inside the battery. And that's what points us to that kind of middle ground. There's a lot of conversation around today around much longer duration storage. People who are looking at some of the iron air batteries that are going to serve hundreds of hours or longer. People who are looking at, either compressed air or storing hydrogen in underground salt caverns that are focused on, maybe hundreds of thousands of hours. And what those technologies share is an unbelievably low cost of the energy storage mechanism. But they're combined with an inability to cycle those forms of storage very regularly.
Sure.
So it's what my friends in the UK love to call horses for courses, right? There are times where you want to have ultra high throughput, and there are times where you want to have an ultra low cost storage medium so that you can pack that energy away and deploy it back onto the grid, weeks to months later.
Nice. Yep. And are you finding, let's say, with the continuing falling cost of solar in particular, but wind as well,
Yep.
and batteries, are you finding that now in most markets that the combination of solar plus storage is cost competitive versus the fossil fuel like gas plants or the equivalent?
It's getting there. Look, our sort of North Star as a business is to be able to generate renewable power, deliver renewable power on demand at lower cost than any fuel-based source of electricity. And we talked a little bit earlier on about the levelized cost of storage as a development metric, and as something we talk about a lot. The reason for that is because of that target. Wind and solar, most regions of the world, you can generate for somewhere between $20 and $30 a megawatt hour right now. If you can, and gas generation, coal generation, et cetera, start somewhere around the $80 a megawatt hour range.
Yeah.
That means you've got about $50 per megawatt hour to play with to take that renewable power and make it absolutely dispatchable. That's that levelized cost of storage number. If you can get the levelized cost of storage down to $50 a megawatt hour or below, suddenly you have a solution that you can deploy to absolutely offset all of those fuel-based sources, eliminate any carbon-producing form of electricity, and use wind and solar plus those low-cost batteries to absolutely accelerate that path towards net zero. That $50 megawatt hour number is notable as well, because that's what the Department of Energy has identified as their 2030 moonshot goal. And we think that two things. First of all, there's very little chance that lithium or some of the incumbent technologies are ever going to get there. But we do have a crystal clear path to get there, and we think we're going to be there about 3 years earlier than what the DOE are projecting.
Wow. And you had an announcement a couple of weeks back that you came out with. Do you want to talk a little bit about that?
We did. Yeah, absolutely. And this is, in some ways, continuing that same thread. The DOE announced back in mid-2022 that they were going to allocate $350 million for pioneering long-duration energy storage projects. We were thrilled to find out that we had been selected for not one, but two of those programs. We were the only energy technology provider that was selected twice. Our program with the DOE is really focused on that levelized cost of storage point, right? They are laser focused on deploying these funds to get LCOS under $50 a megawatt hour to drive that future net zero grid. And through these two programs that we're going to be building with them, we believe we're going to get there, and they've now validated that they seem to think the same thing.
Congratulations.
Thank you very much. Yeah, no, it's tremendously exciting. These projects will see us deploy 84 megawatt hours worth of our next generation product starting in late 2024 or early 2025. We're going to be delivering first 12 megawatt hour array to partners at Pacific Northwest National Labs, who have been one of the preeminent researchers in energy technologies in general and battery technologies in particular over the last few decades. And then we're going to be taking 5 of our initial 14 megawatt hour arrays and delivering those out to a series of rural electricity co-ops who are focused on decarbonizing their local generation and consumption, and using those 5 different sites to really prove in a diverse series of applications how our batteries can go and serve the electric grid. One of the things that we think that we think was really powerful in that application, and the reason that we got selected, not just for the sort of deployment side of their program, but also the sort of the research side of the program, is because our battery is unique in that it combines that long duration capability with that high throughput capability. And so to be able to take a battery, put it out into the field and say, okay, how can we absolutely drive this thing to the nth degree? How do we get the maximum performance out of this? How do we experiment with all of the different things that long duration storage can potentially provide? Because of that, fundamentally non-degrading nature, we're a great platform from which to do a lot of that commercial demonstration. So we are, obviously thrilled at the validation of having DOE stand beside us in some of these projects, and are looking forward to getting them built.
Fantastic. Matt, we're coming towards the end of the podcast now. Is there any question I haven't asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to be aware of?
Yeah, I mean, look, without trying to be, throw anyone under the bus or trying to be too self-serving. I mean, I'd love to just. There's a couple of sort of cautionary notes or things that we've, the missteps that we've seen in the industry over the 28 years that I've been involved with it, that I think is important for people to think about as we're moving into this new mode of starting to deploy this sort of broader set of energy storage technologies. One of them is, there's this interesting interplay between technologies and markets, right? And I often say that, technologies need markets to scale, but markets don't exist until the technology is proven. And there's this chicken and egg thing that we really need to get through. The risk is that you end up pigeonholing new technologies and new capabilities based on what incumbents are already able to do. We're seeing this in some of the markets we serve today, where people see the value of long duration. They know that they're going to need batteries like ours to have their projects deliver the most revenue into the future. But what is paying for those projects right now is a series of markets designed for lithium-ion, and breaking that linkage and making sure that we've got a way of funding broad-scale deployment beyond those narrow market structures is I think critically important, not just for us, but for all of the new technologies that are coming into this space. The other one is rightly or wrongly, no matter what side of the Atlantic Ocean you sit on, the Inflation Reduction Act, I think, has spurred a really critical conversation in our industry around the importance of industrial policy. We, I think, have been very much, we've in some ways have missed the boat in the solar world, for example, right? We've got a very high geographic concentration of where a lot of solar products are being manufactured. And we don't, if renewable energy is going to be, the future of the energy market, which in many ways is the biggest market in the world, all of our countries that we live in need to make sure that we retain an industrial policy, retain and develop an industrial policy that allows us to continue to benefit from, the construction, the manufacturing, and the operation of these products. I think that was a bit of a misstep in the solar world, and I'm hoping that with an increased focus on what domestic industrial policy should look like in the face of the kind of massive upheaval in energy that battery technologies and other renewable technologies are going to drive, that is something well worth considering.
Makes sense. Yep. Cool. Matt, that has been fascinating. If people would like to know more about yourself or any of the things we discussed in the podcast today, where would you have me direct them?
Either one or two things. That you can go to Invinity's website. That's Infinity, but with a V for vanadium, www.invinity.com. Or you can find me on LinkedIn and track me down there.
Perfect. Matt, that's been fantastic. Thanks a million for coming on the podcast today.
Thanks very much, Tom. Always great to chat, and we'll speak to you again.